back into it, and we're just going to start chapter 17. And so we are going to review the reaction of alkenes with alcohol and water under acidic conditions to form ethers. And our two learning objectives are to contrast ethers and alcohols. So this is the ether chapter that we're going into. So what are ethers and how are they different from alcohols? And then recalling some of these syntheses that you've already learned. And then on Monday, we'll start going over new syntheses that you have not learned yet. So let's jump right into it. Learning objective 17A. So we're going to contrast ethers and alcohols. So kind of the beginning of the chapter, just kind of setting up what are ethers. So similarly to when we did thiols versus alcohols, we're going to now compare ethers and alcohols. So ethers are the motif ROR, where that R is going to be some alkyl or aryl group. So it's normally carbon, oxygen, carbon. But one of those carbons is not a carbonyl, right? It's like an alkyl or an aryl group. So because it's ROR, as opposed to an alcohol, which is ROH, right? Ethers have no OH bond. Right? We've just replaced the hydrogen on an alcohol with another alkyl group or another aryl group. So there's no OH bond. That means that we have no hydrogen bonding. So again, just like we talked about with thiols, if you do not have hydrogen bonding, that means that you're going to have a much lower boiling point. Because boiling point comes from those intermolecular forces like hydrogen bonding. So as an example, here is an example of an ether, right? We have that carbon, oxygen, carbon motif. So this is our ether versus our alcohol, right? So we have our OH, this is our alcohol. Here we have our COC, this is our ether. The boiling point of this ether is about 35 degrees C, whereas for this alcohol with the same number of carbons, it's 117 degrees C. That's a huge difference, right? So that hydrogen bonding in the alcohol really, really raises that boiling point, okay? That's very, very similar to what we talked about with thiols. The other consequence of not having that OH bond, it means that there is no acidic proton. We can't deprotonate an ether in the same way that we did an alcohol. You'll see in this chapter, we use a lot of alkoxide, right? O minus. You can't really do that with ethers because it already has two carbon-based substituents. And then the other major difference is that our ether oxygen, so this one right here, that ether oxygen is not nucleophilic, or not very nucleophilic. So that means that even though ethers and alcohols look pretty similar, their reactivity is quite different, because alcohols are often being used as nucleophiles, but in ethers, they're not. Because it already has those two substituents. If it were to lend its electron density to something else, it would now be positively charged. And there's not a good way of getting rid of that positive charge. So because ethers are not very nucleophilic, they're not very reactive, that means that they make great solvents. So you've already learned about this actually in chapter 15 with the organometallic reagents. Professor Roberts mentioned that you use organometallic reagents often in ether solvents. So for example, diethyl ether. Right, so diethyl, because there's an ethyl on this side and an ethyl on this side, and there's an ether in the middle, diethyl ether. You will often see this abbreviated as ethyl 2O. So diethyl ether. You've probably also seen THF or tetrahydrofuran. one that maybe you haven't seen before is called 1,4-dioxane, which looks like that. So these are all really common solvents in organic chemistry, and they are ethers, which makes them good solvents because they're not very reactive, right? We generally do not want our solvent involved in the reaction, right? We just want it there to like homogenize the solution, dissolve things up. Okay, so most of the time, ethers are not very reactive. We often use them as solvents, even for really highly reactive reagents like organometallics. But we've also already learned one example of an ether that is reactive, right? So if we have a reactive ether, they're normally cyclic. Right? So remember we talked about the concept of ring strain, which makes them reactive. So recall we have talked about epoxides. So that's the 3-membered ring. That is an ether. You might also hear epoxides called oxiranes. I don't know why there's 2 names for it, but there are. Most people call it epoxides, I would say. So the simplest epoxide is ethylene oxide. That's the one that we had learned in the previous chapter. We will go into more of these in later this chapter. And it's this bond angle right here, right, that theta, about 60 degrees, that gives it that ring strain. And so that's what makes it reactive, because it doesn't want to have that 60-degree bond angle. If you can open up that ring, now you're relieving that ring strain and allowing it to go to a more favorable angle. So epoxides are by far the most common reactive ether, but it doesn't just have to be epoxides. If you have a 4-membered ring that is an ether that is also highly strained, so this is called oxetane. And again, because it's in a 4-membered ring, you have ring strain. Those bond angles are closer to 90 degrees. And that gives it some reactivity, more so than the acyclic versions. Okay? So that's kind of ethers versus alcohols. Question, yes? Yeah, great question. So why is THF not reactive? So when you get to 5-membered rings and 6-membered rings, they have much less ring strain. So having a slightly larger ring means that the bonds are not distorted as much. Great question. Yeah, so 5-membered rings and 6-membered rings are generally stable. So it's smaller than that, the 3 and the 4-membered rings that are more reactive. And that will come back later in this class as well. Other questions? Okay, so let's recall some reactions that we know to make ethers. So this is our learning objective 17B. Recall the formation of ethers from alcohols, which is 17.5. So there are kind of 2 major reactions that we're going to review here. One of them was from 2301, so section 8.5, where you had an alkene and an alcohol, so methanol, for example, in the presence of acid. So in the presence of acid, the alkene reacts with the acid to form a stable carbocation. So here is a tertiary carbocation, so it's quite stable. And then the oxygen on our alcohol, right, is nucleophilic. So oxygens on alcohols are somewhat nucleophilic, whereas ethers are not. And we're going to quench that positive charge by attacking. And then there's a proton transfer at the end to give us our ether. So there's that oxygen there. Okay, so this is also an ether. Looks a little bit different. Doesn't matter that this is a tert butyl group. It's still an ether because this is still an alkyl group, carbon, oxygen, carbon. So it's still an ether motif. Okay, so that's one way we can make ethers from alcohols, but we also need an alkene, right? So we made our electrophile from the alkene. And then the other way that we've learned, we just learned last chapter in 16.7. This was the reaction where we had a primary alcohol. Remember, primary means the carbon attached to the OH has 2 hydrogens on it. This is a primary alcohol. Under acidic conditions, so like H2SO4 and heat, basically the same conditions as above. So here's our acidic conditions. We made ethers that were symmetrical, right? So this is an ether, and this group is the same as this group. So we talked about how the limitations of this reaction were that it only works for primary alcohols. Because remember, if you use secondary or tertiary, it wants to do E1 elimination instead, right? So this only works for primary alcohols. And it only works for symmetrical ethers. So I want to talk about that one a little bit more. Why is it only symmetrical ethers? Because that makes it really important to differentiate when you might use this reaction versus the one we're going to learn next week. Okay, so why? So let's do a thought experiment. If I were to, instead of just putting in 1 alcohol, I put in 2. So if I put in ethanol, right, it has 2 carbons here, and then I put in propanol, 1, 2, 3 carbons, could I do this reaction? So what would happen? So first, we have to check, are these primary alcohols? Yes, here, here. They both have 2 hydrogens on that carbon. So we have 2 primary alcohols, so that's good. So what happens if we run this reaction? It should work. The problem is that you get a crazy mixture of products. So we might get the product that we want, which is this mixed couplings. We have 2 carbons on one side and 1, 2, 3 carbons on the other. That would be taking 1 of the ethanol and 1 of the propanol and putting them together. We probably will get some of that. Unfortunately, you never just have 2 molecules in a flask, right? You have a bunch of each of those molecules in a flask, which means in addition to this product that you want, you will also get 2 carbons on each side and 3 carbons on each side. So you get this mixture. And those are going to be really hard to separate because they're very, very similar. Okay, so why does this happen? So if you remember the mechanism of this reaction, right, we needed to generate an electrophile by protonating one of our alcohols, and then the other alcohol comes and attacks it. So if we have these 2 alcohols, you can ask yourself, like, which one is going to be the electrophile? So could I make the first one into an electrophile? Yes, right? I can protonate the first one and make an electrophile. I could also protonate the second one and make an electrophile. Right? If I protonate this one, they're basically the same, right? So that means that either of our alcohols can be the electrophile. What about the nucleophile? again, alcohols are nucleophilic, so I could have my 2-carbon alcohol be the nucleophile, or I could have my 3-carbon alcohol be the nucleophile. So again, either of them can play either role. So that's why you get this crazy mixture and you can't actually control which product you're getting. So this is why the acidic conditions of 2 alcohols coming together, you only want to use that when making symmetrical ethers. Questions on that? All right, let's do a chime-in question to see if that's making sense. Okay, so we're talking about that reaction we just talked about. So under acidic conditions, which of these ethers can you make in high yield, so not in a crazy mixture, from alcohols, under these acidic conditions? More than one can be correct. So we'll give you a couple minutes. Feel free to chat with your neighbors. So just think about those 2 limitations of this reaction. Do 10 more seconds to get in your answers. All right, let's see what we got. Nice, okay. So yes, most people are getting it. So it's A and D can both be made. Some people are thinking B, which I get. It's also a symmetrical one, but it's secondary. So let's go through each of these together and look at why only A and B, or A and D, are possibilities. So you were given 2, 3, 4, 2, 3, 4. This, and this. Okay, so for each of these, we need to go down the 2 limitations to see if we can make them. So the first one is, are they both primary? So here and here, we have at least 2 hydrogens here, right? So those are primary, right? And is it symmetrical? Yes. Great, so that one works. The next one, here, there's only 1 hydrogen there, right? Carbon can't have more than 4 bonds. So these are secondary. Those would have to come from secondary alcohols. So that is not going to work. So if you're only thinking about the symmetrical one, yes, this is symmetrical, but it's secondary, so you can't do it. Okay? So you have to look at both of those criteria. Next one, here and here, primary or methyl in this case. Yes, that's fine. Is it symmetrical? No, right? So no, that one doesn't work because it's not symmetrical. And then finally, we look at this one. Again, we have 2 hydrogens on each of those carbons. Good. That means, would they come from primary alcohols? Yes. Is it symmetrical? Yes. So that's why this one and this one works. Okay. So under acidic conditions, so this is the acidic conditions way of making ethers from alcohols, you need both primary alcohols and symmetrical. Okay, so always look for those 2 factors. On Monday, we will talk about the basic condition ones, which you can get unsymmetrical. Okay, questions on this? Okay, that's all the content that I wanted to cover